So this question, which is question number 4 in section 2.4, is a lot like the last problem we did in the previous video. So if you want more information about how to answer this type of question, you can actually go to the book on page 87, and it talks about how to interpret the standard deviation of a data set by looking at a graph of that data. And in example 5, they go through examples. So for example, it tells you without calculating, estimate the standard deviation of each data set. And then they go through the solution. So what I do want to mention before we move on to our next example is what are called unusual and then very unusual data values, right? So what makes a data value unusual and what makes a data value very unusual? Okay. Okay, it says at the very top of this paragraph at the bottom of page 87 that data entries that are more than 2 standard deviations from the mean are considered unusual, while those that are more than 3 standard deviations from the mean are very unusual. Okay, so we're going to use that information to answer some questions for the next topic that we're going to talk about in this section. So let's go back to the homework, and we're going to go ahead and go on to question 5. Okay, the problem says to use the empirical rule that says that the mean speed of a sample of vehicles along a stretch of highway is 64 miles per hour with a standard deviation of 5 miles per hour. And it says that we want to estimate the percent of vehicles whose speeds are between 49 miles per hour and 79 miles per hour. And it says in parentheses to assume that the data set has a bell-shaped distribution. Okay, so in order to answer this question, we have to know what the empirical rule is for bell-shaped data. So for that, we're going to go back to the book and go to the next page. Okay, and at the top of page 88, it says that many real-life data sets have distributions that are approximately symmetric and bell-shaped. Okay, so let's start over again. So many real-life data sets have distributions that are approximately symmetric and bell-shaped. So for instance, the distributions of men's and women's heights in the United States are approximately symmetric and bell-shaped. Okay, so for example, if you were to create a histogram of the heights of men in the United States, so for example, this histogram are the heights of men in the US, ages 20 to 29, you can see that the histogram has a bell shape to it, and it's symmetric. Okay, kind of like what this graph looks like. So this is a graph that's perfectly bell-shaped and symmetric. So later in the text, you will study bell-shaped distributions in greater detail. But for now, however, the empirical rule can help you see how valuable the standard deviation can be as a measure of variation. So if you look at this diagram carefully, all right, it tells you the percentage of data values that you are expected to see within a given number of standard deviations from the mean. So for example, for data that are bell-shaped and symmetric, the mean of the data is going to be in the middle. Okay, and that's where the peak of the curve is. Remember, the peak of a curve is the highest point. Okay, so the mean of our data set is right here in the middle. So approximately 34% of the data is within one standard deviation to the left. Likewise, because the curve is symmetric, right, approximately 34% of the data is within 1 standard deviation to the right. So basically, about 68% of data values are within 1 standard deviation of the mean. Okay, so this line here, you may not be able to see it in the video, but this line here is 1 standard deviation to the left of the mean. Okay, this line here is 1 standard deviation to the right. Okay, this is 2 standard deviations to the left, 2 standard deviations to the right, so on and so forth. So you have what's called the empirical rule, which or the 60, 95, 99.7 rule, which says that about 68% of the data are within 1 standard deviation of the mean, 95% of the data are within 2 standard deviations of the mean, and then approximately 99.7%, which is almost the entire data set of the data are going to be within 3 standard deviations of the mean. So for data that are bell-shaped and symmetric, these values, right, 68%, 95%, 99.7% don't change. Okay, but what will change are what the mean and standard deviation are. So let's go ahead and look at this problem once again. Okay, and it says to use the empirical rule, and the mean speed of a sample of vehicles along a stretch of highway is 63 miles per hour with a standard deviation of 4 miles per hour. And we're going to use that information to estimate the percent of vehicles whose speeds are between 59 miles per hour and 67 miles per hour. And once again, it says that assume the data are bell-shaped and symmetric, or that the data have a bell-shaped distribution. Okay, so what we're supposed to do is we're supposed to use the information given in the problem and use what we know about the empirical rule to answer the question, right? So we're going to determine approximately the percentage of vehicles that travel between 59 miles per hour and 67 miles per hour along this stretch of highway. All right, and we want to make a note of the mean, which is 63 miles per hour, and the standard deviation, which is 4 miles per hour. Okay, so I've copied over the diagram for the empirical rule from the book. So you want to notice what each of these symbols represents. So X bar is going to represent the mean. Okay, so the symbol X bar looks like an X with a bar on top of it. And then the letter S will represent the standard deviation in our problem. Okay, so the mean is equal to 63 miles per hour. So in our diagram, I'm going to label underneath the symbol X bar, I'm going to put the number 63 there. So that's where we know where the mean is in our graph. Okay, so that's the location of the mean in our graph. Okay, so what we need to do is fill in the rest of these values. So these values here represent the values that are 1 standard deviation to the left and 1 standard deviation to the right. So the standard deviation is 4. So if we do 63 minus 4, we get this value, 1 standard deviation to the left. So 63 minus 4 is 59. Okay, so this value over here to the right is 1 standard deviation to the right, so that'd be 63 plus 4, which is equal to 67. Okay, and then we need to figure out the other values. Okay, so this value over here is 2 standard deviations to the left of the mean, so we're going to do 63 minus 2 times 4. Okay, we get 55. So 55 here is 2 standard deviations to the left. Okay, and then we're going to get the value 2 standard deviations to the right, so it'll be 63 plus 2 times 4. Okay, which is equal to 71. Okay, so 71 is 2 standard deviations to the right of the mean. All right, and lastly, we're going to get the two values that are 3 standard deviations to the left and 3 standard deviations to the right. Okay, so all we need to do is subtract 4 from 55 to get 51. So 51 is 3 standard deviations to the left of the mean. Okay, and then 71 plus 4 is equal to 75. So 75 is 3 standard deviations to the right. So once we've correctly filled in our diagram, okay, according to the mean and standard deviation, we can now answer the question. Okay, so the problem was asking approximately what percentage of the vehicles travel between 59 miles per hour and 67 miles per hour. So, okay, so between 59 and 67 miles per hour. Okay, 59 is here, 67 is here. Okay, so 59 is 1 standard deviation to the left, 67 is 1 standard deviation to the right. Okay, so we're simply going to add these percentages inside the curve. So 34.13% plus 34.13% is going to be our answer. Okay, so 68.26%, so approximately 68% of the vehicles, okay, have a speed, okay, that is between 59 and 67 miles per hour. So we don't need to write our answer, but I'm writing out the answer for clarity. Okay, so this is what the 68% represents. It's the percentage of vehicles whose speed is between 59 and 67 miles per hour, according to the empirical rule. Okay, so our answer is going to be approximately 68%. All right, let's go ahead and look at the next question. Okay, so in question 6, it says that the mean value of land and buildings per acre from a sample of farms is $1,200 with a standard deviation of $100. And it says the data set has a bell-shaped distribution. And it says assume the number of farms in the sample is 78. Okay, so part A says we want to use the empirical rule to estimate the number of farms whose land and building values per acre are between $1,100 and $1,300. Okay, so to do this problem, I've copied over the diagram for the empirical rule, and then I've summarized the important information. In other words, the mean is 1,200, and the standard deviation is 100. Okay, so we're going to use the mean and standard deviation to label the horizontal axis of the graph here. Okay, so the mean will always go in the middle. Okay, so the value that's one standard deviation to the left would be 1,100, okay, or 1.1k, and the value that's one standard deviation to the right would be 1,300, or 1.3k. Okay, so in other words, I'm abbreviating here since I can't fit the values if I write them all out. So 1.1k is 1,100, 1.3k is 1,300, okay, so on and so forth. And then I've labeled the values that are 2 standard deviations to the right, and then 2 standard deviations to the left. Okay, so the question was asking, right, so we're going to use the empirical rule to estimate the number of farms whose land and building values are per acre between 1,100 and 1,300. Okay, so according to our diagram, right, 1,100 and 1,300 are within 1 standard deviation. Okay, and remember, so 34.13 plus 34.13, okay, is approximately 68.26%. Okay, so to get the number of farms, right, that are between these two values, okay, we're going to take 68% and multiply by the number of 78. So 78 are in our sample. Okay, so we're going to take 68.26% of 78. Okay, well, how do we do that? Well, we need to convert the percentage into a decimal. So the percentage, when you convert it into a decimal, you divide it by 100. Okay, which is 0.6826. Or in other words, take that number, or the decimal point, move it 2 places to the left. Okay, multiply that by the number in our sample. Okay, we get approximately 53. So approximately 53 farms are between $1,100 and $1,300 per acre. Okay, part B says, if 26 additional farms were sampled, about how many of those additional farms would you expect to have values between $1,100 and $1,300 per acre? Okay, so remember, between 1,100 and 1,300 is about 68%. So we're going to take 68% as a decimal and multiply by 26. Okay, round it to the nearest whole number, so that's 18. So we're going to put as our answer, so 18, and we're going to check it. and that's correct.